In this section, we're going to do something that's actually quite similar to what we've done in the first section for this week with D3 regression. We're going to use a D3 library or D3 related library to calculate the layout of, or the positional kind of attributes of our visualization, and then we're going to use Svelte and Florence to actually do the visualization and to draw things on the screen. The particular layout that we're doing in this section is a network layout, a network visualization, and they're a little bit tricky or finicky, if you will, because they don't have sort of inherent explicit positions, because a network, a graph, consists of nodes and links between them. And if you're in the Urban Science Masters, I think you've discussed sort of similar things when you talked about multidimensional scaling, for example. So there's no absolute position of nodes in a network, but we can do relative positioning, and that relative positioning can be done in all kinds of different ways. There are all kinds of algorithms for that. If you search online for this, you'll find many different algorithms. You also find many different implementations of these algorithms in JavaScript. Here we're going to use a graph layout algorithm that's implemented by Mike Bostock and sort of implemented in a D3 kind of related manner. So the algorithm is available in this d3-force package, and what we're going to do is basically replicate this completely D3 based approach with a combination of using D3-force and Svelte. So this is also a nice exercise in that sense, in taking an example that we find and adopting it or adapting it to our kind of the technologies that we use and the specific needs that we have. So to do that, again, I have set up a starting sandbox. I have that here open as well. There we go. It's a very simple sandbox. We have an app.svelte, as we're quite familiar with now, with an empty graphic, some basic imports from Florence, the actual data import. So this is the same data as is available here in this notebook. It's actually, if you scroll down, there it is. There's this miserable.json. We'll talk a little bit about that data set in a second. And then we're also importing a bunch of functions for simulation, force link, force many-body, etc. from d3-force. So I've pre-installed the d3-force library here as well. So what we're actually doing is we have this data set, as is mentioned here, of character co-occurrence in Les Miserables. So that means that these characters are probably in the same scene or in the same chapter or whatnot. And the more often they co-occur, the higher the intensity of the link between those two characters is. And what we want to do with an algorithm like this, generally speaking, is we want to make sure that things that have a strong link, right? So in this case, characters that that kind of co-occur a lot together, we want to place them closer together, and characters that have nothing to do with each other, we want to separate them kind of spatially a little bit further. And apparently, as we can see here, this particular algorithm allows us to do that. So how do we actually go about doing that? Basically what I'm going to do is I'm going to kind of copy over this logic, but you will see we'll have to kind of append it, and you also see we will simplify it a little bit as well. So we're going to, let me see here. We start with, here too, the data seems to be called data. We have that as well. We have our data. Let's just actually start with having a look at that data file. There we go. Just to know what we're dealing with. So it's displayed here in the console, and it looks like it's an object, and the object has two keys, nodes and links. And just to have a look at what a node might look like. So a node here is just has an ID of the name of the character, and there's some group information too that we might later be able to use for coloring, etc. And then the links, there are more links than nodes. There are 77 nodes. There's about 250 links. And the links, as we can see here, have a source, so one character, and a target, another character, and then they have a value too, which we can see here changes from 1 to 10, etc. So that's the strength of the link there. All right, so let's see what we're doing here in the original notebook. So the first step here is to set up two variables that we call links and nodes. And basically what they're doing is they're extracting from the original data the links and the nodes, because as we'll see in a little bit, we want them to be separate, and we also want to change them up a little bit. So what we're actually doing here is we're making copies of them so we don't affect the original data. So we can do that too. We can say let links equals, and then I'm going to use a slightly different syntax because you're already familiar with this particular syntax. It's the spreading syntax, and basically what this will do is this will make a direct copy of these two, whatever is in these two keys. There we go. Without affecting the original data. We can, as always, do a quick check. Let's just console log the nodes. And there we go, right? So we still have 77 nodes, and then each entry is that has that ID and that group. All right, so now we have that set up. Let's see what is happening next. So the next thing here is that we set up our simulation, and this is important to note here, is that as you can see when we load this page, it's actually a dynamic algorithm, an iterative algorithm that updates itself at specific steps until it reaches kind of a stable state. So I guess that's why it's referred to here as a simulation. I'm going to copy over this particular logic, and then we'll adapt it a little bit. There we go. So let's see what we need to do. So in the original example, and you'll see this a lot, the entire D3 library is imported with all of its kind of utilities that are available within it. We do this more directed import here. So we also have force simulation and force link, etc., but they're imported specifically by reference. So we don't need to have this kind of prefix. So we will remove that, otherwise it won't. We don't have that D3 object available. So we just need to remove that. All right. There we go. Now, once I run this, you will see. Let's just log it here. You will see that we get an error because here it says width is not defined. Before we actually talk about what is actually happening here in all of these steps, you can see here that it uses a variable called width and height. Those are just going to be the width and the height of our visualization. So I'm going to create those as well. Okay, there we go. So now we should no longer have that error. There we go. So now this console log here refers to the simulation, and apparently there's a bunch of things available within a simulation. So let's run through each of these steps here because they're not discussed at length in this notebook, but they are. Each of those functions are available in the API reference. What we're doing here is the first step is actually setting up the simulation. So that's similar to when we previously have imported, let's say, skill linear, and we start kind of creating that linear scale. So that's the first thing we do. We set up this simulation or this layout algorithm, and we feed it the nodes. Now the nodes we had created here, right? Now it only knows something about nodes, but we also need to tell it how do you connect the nodes? And another word for connecting is linking. So here we're going to set up the links of the simulation, and we do that based on the links dataset available here. And we also need to, this is kind of like a join, if you will, that we're familiar with from both the data container as well as the tidyverse dplyr library. We need to say what is the common attribute in the node dataset and in the link dataset so that we can actually tie them together. And in this case, you might remember that we have this ID here that refers to the name. So that's what we are referring to here. So this allows us to import the nodes, link them to the links, and that's basically the setting up the data. These next two steps are to actually set up the kind of the layout algorithm. In this case, we're using this force many body function. Now, if we go to the simulate or the documentation here, what was it? Force many body. There we go. We have this whole section here that explains it. Basically, what this particular function or this particular algorithm does is it will use kind of a gravity-based approach, so that if a link is strong, the two nodes will draw closer together. If it's weak, the links will be further apart. So that's what we set up here, apparently, but you can find out more about this in the documentation. There might also be other types of functions we can use here to set up this charge. And then finally here is we need to somehow give an anchor point to the entire layout, and we do that here by setting the center to be halfway of the width and halfway of the height, right? So that will actually put the center of the nodes, or the center of gravity, if you will, in the very center of our visualization as well. All right, so that in principle should set up our entire layout algorithm, but we haven't actually drawn anything yet, right? So how does that work? Now, first, let's take reference of what is happening here. In this complete D3 example, we use the kind of D3 DOM manipulation techniques to then set up these actual links and the nodes, and then whenever the simulation updates, we also will update the attributes x1 and y1, etc. of all of these links. Now, we don't need to do that. We can simplify things a little bit further. To do that, let's first actually inspect the nodes object here. Oh, I had it here already too. Let's just remove that so we can see it. What's happening is that we feed this layout algorithm the nodes and the links. As it's calculating the layout, it will actually add information back to those original objects. So when I console log nodes here, once I open it, you will see here that it now not only has an ID, but it also has an X and a Y and then some additional information as well. Now this X and Y, that's actually the information that we need to visualize. So we can now start doing that. So what I'm going to do is I'm going to create my graphic, and hello. I'm going to make sure it is the same width and height as we had previously established. There we go. So this is referencing those variables that we had created up there, right? And then within the graphic, I am going to loop through my nodes, and then set up the closing of that loop too. There we go. And then I'm going to create a mark for every single node. I could use a point layer, for example, as well, but I'll use this now to keep things a little bit simple. So I'm going to create a point. I think point is already imported here as part of the sandbox. And there we go. And then, as you remember, a point needs two properties, x and y. And those two properties are part of the node. They are here called x and y as well. So we can say node x and node y. And once we save, we see something happening here. So something is actually visualized, something is actually plotted, but it doesn't quite look right. It doesn't look at all like the original example here. Now, why is that? That is because this particular algorithm works in an iterative way. When we draw this point here, it does so at the very start. All of these nodes are placed for some reason here in the upper left corner. The algorithm afterwards is updating the nodes in that data set, but Svelte actually doesn't know about that, so it will also not update here. What we need to do is we need to somehow tell Svelte that this particular variable has been updated. Normally we do that by making reference to a variable, and then Svelte will actually see that here in our code, and it will automatically kind of update here. But we haven't done that yet. We have not, apart from here, it would look like the nodes have never been changed, right? After line 10, these nodes are never touched again. That happens inside of this function, which is a little bit sneaky, so Svelte doesn't actually know about that. So we need to basically tell Svelte about this. To do that, there's two key ways to do that. Here we can see that in this example too, what we do is we access the simulation and then we say on, and then we use this tick word. So what is that actually? Now if we look at the tick, there's a lot. Oh, there we go. Yeah. If we look at the documentation here, we see that we have this on method, and then we have a type name, and then whatever we want to do. It's kind of like an event listener, if you will, but the events are not mouse clicks or mouse overs, but they are one of the two of these following. One is tick and one is end. So tick is after each tick of the simulation's internal timer. So that is each iteration of the simulation will generate basically this tick event. You can do something like update your visualization, and then the next tick comes around, you can then update the visualization again. So it's basically like a step. We also have end, and that is after the simulation's timer stops. So when it's kind of reached a stable layout, it will basically fire this end event. So let's use that end event first. So to do that, let's see here, we say on, and then we have to give the name of the event. So in this case we will use end, and we then give it some kind of function to execute. So I'll just use this anonymous function here, and what I'm going to do, just to make sure that things are working, I'm gonna console log and say the layout is finished, and then this will give you a nice insight into what's actually happening. So here, once I save, you'll see that this visualization is there, but we're still waiting for that console log, and there it is, right? So it takes, what is it, 2-3 seconds or so for that visualization, or for the layout to actually be completely done calculating. Once that's done, we need to tell Svelte that this nodes data is actually being updated. But it's already, the information is already there, so we use kind of a little bit of a shortcut here, and we just sort of reassign or re-reference the nodes variable. So this doesn't actually do anything, it doesn't actually compute anything, but it's just a little reference for Svelte to tell, hey, the data has changed, make sure that you update the DOM that depends on that particular data. So once we do this, what we'll see is still static here, but once we see this console log saying that the layout is finished, there we go. Then our layout is actually finished. So this looks already quite good, because if you remember the original website, that's pretty much the same shape, right? So we're on the right track. One thing we can do is, instead of listening for the end event, so that's all the way at the end, we could just listen for the tick event, and then let's get rid of that console log because we don't need it anymore. Once we do this, what we should see is similar to the original visualization. On every tick, the position of the nodes is updated until it reaches this stable point. So we're almost there. All we need to do is copy this same logic, but instead of creating points for the nodes, what we want to do is we want to loop through the links dataset, and then for each link we don't want to create a point, but we want to create, of course, a line. And then if you remember from the example, you might have seen this, we are here we're setting the line where we use x1 is source x, x2 is target x. So we need to use that same logic to access the right x and y. Actually, let me just show you here what that actually looks like. So we console log the links here, and then there we go, we have 255. We just look at a single link. There you go. So we have a source, and that source has an x and a y, and we have a target, and that target has an x and a y too. So that's what we need to access. So to do that, uncomment this again. All right. We need to, so we're creating a line, and in kind of the Florence way, we want to give all of the x coordinates to that line. So instead of a single coordinate, I'm gonna, in this case, give 2. It's similar in that sense to the regression line that we created earlier. And the first coordinate is the coordinate of the source, and the second coordinate is the coordinate of the target x. There we go. And then let's just copy this. There we go. And remove this. And then we replace the second one. We replace all the x's with y's. And then maybe also, we don't want the lines to be too thick, so I'll just change the stroke width here already. I think that defaults to 3, but it might be a little thick here, so let's see. Yay, there we go. So now we have our graph layout visualization. Of course, we could add colors, etc., but I think the principle is clear. So basically what we did is we've taken all of this D3 based logic, and we have extracted the key parts for us, and that's basically importing the data, splitting the data into links and nodes, because those two things are important to keep separate for this particular algorithm. We invoke the algorithm or the function with force simulation. We feed it the nodes. We then set up the links between the nodes and specifying the ID as the kind of common attribute. We give it a charge function that determines how nodes can repel or attract each other, and we give it an anchor point for the visualization in the center of our graphic, the midpoint of our graphic. And then we do one little extra thing, is basically we say on every tick, we say to Svelte, hey, this node and this link variable has updated by making a reference to it, and then Svelte knows enough because then it will automatically update whatever is depending on that variable in the DOM. And that's creating a graph with d3-force.